Hello everybody, thanks for attending this session. In this short presentation I want to draw your attention to an exceptional sensor for blade and tower loads we have brought to the wind energy community recently. So why did we develop it? On our way to a comprehensive turbine health and usage monitoring system, looking at the most important main system for wind turbine efficiency, the rotor, we became aware of certain difficulties of the current mainstream sensors for load measurements, the strain gauges, with this specific application. So we felt a sensor significantly more apt for this task was required. Strain gauges capture constant and intermittent load components. Acceleration sensors do only the latter. So our sensor would have as a minimum the same detection range and quality as have strain gauges. Strain gauges installation is delicate and rather difficult. It's required to be precise. Our sensor would need to have a robust design and to be easy to install for any trained wind turbine technician. Strain gauges cover only a small area, so local composite inhomogeneities affect their measurements. We would rather go for a wide area measurement sensor that would not be prone to local inhomogeneity. Strain gauges are fixed to the surface and degrade over time through creeping. This is something that we would definitely want to avoid. We wanted a force-free measurement which has no degradation over time. And the last thing is that strain gauges require elaborate temperature compensation, and you would think there must be a solution by simple thermal strain compensation through material match. So how does the sensor work? To the inside of the rotor blade surface, we fix the cantilever support, which in itself carries the cantilever tube. To the end of the cantilever tube, we fix our target. On the other side of the sensor, there is a high-resolution proximity sensor with its own support. The length of this sensor is either extended by the moments or compressed by the bending moment of the rotor blade. And this is being measured by the proximity sensor. This is the way how the sensor would look like if it's fully installed in the blade without its step protection cover. We've now made a couple of installations and can judge the design as well from a practical point of view. The following characteristics are worth highlighting. We can adjust the thermal elongation according to the object that we're supervising by changing the cantilever materials. Could be titanium, carbon steel, CFRP, or others. The sensor is based on standard industrial sensors, so it's not something awkward. It has a 4 times higher noise signal ratio than do have strain gauges, so we have more precise measurements. The lightning protection is really proven by a harsh industrial test, so we can guarantee that there is no problem. And the technicians installing the sensor improved the process so much with their fixture that they developed for the installation, so it's really easy now to install. So what could be possible use cases? The plot on the right shows the flat-wise normalized bending moment of a 2.3 megawatt turbine over 20 minutes. The sensor values shown can be used directly for blade load management through individual pitch control. Combined with SCADA data and artificial intelligence, it will be even possible to avoid high gust blade loads in the future. If you plot normalized flap against edge moments, you get orbitals representing the trajectory of the respective blade axis. These orbitals are characteristic for the respective load range, but too complex to be analyzed in real time. They can be used, though, after calculating the average center to form blade-specific operational KPI curves, which then can be used for analyzing if they are close to identical between the blades or not, and as well for analyzing if they change over time. If they are not identical between the blades, there could be a pitch issue, or the blade was mounted with one hole difference, or the 0-degree marking is stamped wrong, etc. Changes in the blade-specific KPI curve would make you aware of blade aging or pitch system deterioration. Cantilever sensor data combinations with SCADA allow additional curves with more options. In the upper graph, you can see wind speed over a 5-day period. In the lower graphs, you see the classical power curve developing together with 2 flap moments versus SCADA data values. I will now accelerate the issue a little bit, and you can see how the individual flap curves develop. and how the moment, the flap side moment, is reduced by pitching. These or other SCADA data correlation curves together with algorithms allow you to detect slow performance changes of your rotor system. A second use case is the detection of structural changes. The case shown here is from a 2.3 megawatt turbine having a known leading edge delamination on one blade. The yellow marked time range is the repair period. Comparing signals between two blades each, the damaged blade is easily detectable in the green curve. The yellow one is hidden behind the green one, versus the blue one for the two intact blades. This approach needs a definition of an OK status up front for all blades. Here we did it after the repair was completed and then recalculated. Currently we are working on algorithms for ice detection and have had some really promising results so far. The last use case I want to present is load supervision by rainflow counts. The graphs show bins of flap and edge moment counts per month, which accumulate at characteristic plots per blade or turbine over longer periods, here a year. These can be online decision tools for which turbine would be better given a break in high wind curtailing or would need a preventive maintenance action. These load diagrams as well are an excellent end-of-life decision basis. I hope I could generate your interest for this specific sensor, which can be used as well in towers or other structures. We think it's well worth knowing more about it. We are looking forward to your questions. Thanks for your time.